Hey everyone, welcome back and let's write some more Leetcode today. So today let's solve the problem, power grid maintenance. And of course, somebody on the Leetcode team must have thought they were writing like a 5-paragraph essay or something, but I'll try to give you the short version of this, just focusing on the examples. So the idea is that we're given a parameter C, and that's going to determine the nodes in our graph. They don't explicitly tell us this, but they talk about edges and connections and stuff like that, so it becomes pretty obvious. Now, the graph isn't always going to look like a linked list like this, so keep that in mind, and keep in mind that the edges are going to be bidirectional. We're given the edges in a second parameter. Now, also remember that this parameter is going to be 1 indexed, so the nodes are going to be, so if C is 5, nodes are going to be 1 through 5. Every node is going to have a unique identifier. And so initially, we can say that all of these nodes are online. What does that mean in the context of this problem? Well, you can read it if you care, but I don't really care. So let's say initially all of these are online. Let's just run through the example. Well, we want to answer a bunch of queries, and there's 2 types of queries that they give us. And we can determine which one based on the first value of that query. So each query is going to be a pair of values. The first value is going to be 1 if it's this type of query. It's going to be 2 if it's this type of query. The second one is a lot easier, so let's start with that. So if we see a query like this one over here, 2, 1, that means it's the second type of query. We go to node 1 and we take it offline. That doesn't mean the node doesn't exist anymore. It just means it's not online anymore. When we do that type of query, we don't do anything. We don't need to return any sort of result. But when we have the first type of query over here, 1, 3, then what we want to do is go to the node 3, and we want to ask the question, is 3 online? Because if it is, then the answer to this query is going to be 3. And in this case, it is online. So that's why you see in the output, the first value is 3. So we answered that query with a 3 value. What's going to be next? Well, that was the other query that we already went over. And remember what I said, that one, we don't need to answer it. We don't need any output value for the 2 type queries. Okay, next we have this one. So remember, this one went offline. So now we're here, 1, 1. So it's the first type of query, and we go to node 1, which does exist, but it's not online. So now, if it's not online, the answer cannot be 1 of this query. So now, to resolve this query, what we do is ask, since it's offline, we want the operational station with the smallest ID that's in the same power grid as, in this case, 1. If no operational station exists, then we return -1. So what do they mean by power grid? That's kind of what I glossed over at the beginning. But in the context of this problem, it's basically going to be a connected component in terms of graphs. If you don't know what a connected component is, I would highly recommend learning a bit more about graphs. Plenty of resources for you to do so. I would check out Leetcode.io if you like my teaching style. I said connected graphs, but what I meant is connected component. And that just means that these stations are directly or indirectly connected via edges. So in this problem, it's really kind of simple because we just have like a linked list. So this is just a single connected component. But imagine that maybe this edge didn't exist. Then we would have started with 2 connected components like this. And of course, the connected components could be more interesting. They don't have to be a straight line. We could have something like this and maybe something like that. So I keep that in mind. But in this example, it's pretty simple. So I'll try to finish this one. So among all of these, which one has the smallest value, the smallest ID that is still online? Well, in this case, it's 2. And one way we could figure that out is maybe just starting from here, running some kind of graph traversal on this connected component. It could have been a DFS or it could have been a BFS. Maybe it's not the most efficient because we would have to iterate over the entire thing, but it is a possible way to do it. So the answer to that query is going to be 2. So that's what we're going to put in the output. And then finally, we have another query over here. We're going to take now 2 offline. So get rid of 2. And then we're going to have this query. It's the first type of query, and we're going to node 2. So we're here. What's the smallest ID of a station that's still online? In this case, it's going to be 3. So we will put 3 in the output, and that's what the output is. You can see here it matches. Okay, so now we know what we're trying to do, but how exactly do we do it in terms of making this efficient? Well, first of all, recognize that we're going to have to convert this list of edges into a way for us to actually traverse the graph. And we can do that by converting it into something called an adjacency list. And if you're not familiar with that, I would definitely probably not attempt this problem just yet, to be honest. So that's what we're going to do. It's a pretty trivial step. We just use a hash map. Once we have that, we want to be able to separate the nodes, because this example is really simple, but imagine we have something like this. I have a 6 node, I have a 7 over here, I have an 8 over here. So now we have 2 connected components, that one and that one. We need to be able to differentiate these nodes from these nodes. I guess you wouldn't necessarily have to, because it's true in the naive way where every time we're just given some node, we immediately go to that node and maybe we then run some kind of traversal on it. It's pretty much expected that we're never going to land on any node outside of that connected component if we're DFSing or BFSing. But ideally, we wouldn't have to run a traversal every single time like that. Is there a faster way? Because for every connected component, can't we just track the minimum online node? Because if we track that, then we can always return the query very quickly. We can pretty much answer each query in constant time. Now, we could, but it's not going to be quite that simple, because imagine something like this. Imagine for this connected component, we have 6, 7, and 8. What if we tracked, okay, the minimum right now is 6, and that's fine. And maybe we remove or take 7 offline. So 7 is offline now. Okay, well 6 is still the minimum. That's fine. But now we take 6 offline. Okay, now how do we find the new minimum? It's not trivial to do that. We might have to run a brand new traversal on the graph, because we can't just say, okay, well, it's going to be one value bigger now, because actually 7 doesn't exist either. 7 is offline as well. So it has to be 8. There's no easy way for us to figure that out. And that's why we're not only going to track the minimum value, we're actually going to put all of these values into a min heap, because that way things will naturally work out. And this is roughly how it's going to work. So imagine all these 6, 7, and 8 are in the min heap. So I'll just kind of draw it like this. So let's run through that exact same scenario I talked about just a second ago. What's the minimum right now? It's 6. And we can get that in O of 1 time, because this is a min heap. We're not going to be removing it. We're just going to be reading it. So that works. Okay, now what happens if we removed 7? We took 7 offline. Well, first of all, we have to mark that somehow. And your first way to do it would be probably to think of removing it from the min heap. But it's not so trivial to do that, because a min heap, it's going to require us to remove 6 before we can remove 7. And we don't necessarily want to remove 6. So a better way to do it is, I guess I would call this like a lazy delete, because we're going to mark 7 as deleted. But we're not going to mark it as deleted from the min heap. We're going to use another data structure. My preference is to use a hash set. So what I'm actually going to do initially is just add all of the stations initially to the hash set, which I'm going to call the online hash set. So now we can immediately know for any node, is it online or not? And so when 7 goes offline, all we do is remove it from the hash set. That's going to be a really quick operation. But now, when it comes time to make another delete, and before I run through the case where we delete 6, right now, if we wanted to get the minimum from our min heap, it's still going to be 6, and that's fine because 6 is online. But now, suppose we remove 6 from the min heap, and once again, we're actually just going to do a lazy delete. Not because we necessarily have to in this case, because that actually is the minimum, but just because it's going to make the code a bit nicer. So still a lazy delete. We're only going to remove 6 from the hash set. But now maybe we go to 8 and now we query it. We ask, like, what's the smallest station that's online in this connected component? Well, we're going to go to this min heap. We're going to have a min heap for every single connected component. And now we're going to check. Well, is 6 the smallest? Because 6 is the smallest in the min heap, but 6 is actually not online. So we're just going to pop 6 and not do anything with it. Next, we're going to do the same thing with 7. Is 7 online? Nope. Get rid of it. And finally, we'll go to 8. 8 is online, so that's what we would return. This seems kind of complicated, so let me make it very clear why we're doing this. Because what we did just now is, in the worst case, we're going to possibly have to pop from this min heap. And obviously these values are going to be pushed as well. But that time complexity is going to be like the size of the connected component, which in the worst case, I think would be n if we just had one really big connected component. I guess I'll use the variable c because they give that to us. So in the worst case, it'll be c. And Pushing and popping from a heap is going to be log C, so that's not super bad. Compare that to before, where instead of having a heap, every time we run the query, we have to traverse that entire component, check each node. Okay, is this one online or is it not online? We could do that with the hash set, sure, but if we did it that way, for each query, we'd have to traverse the entire component, which would be C. How many queries are we going to have? It's going to be, in the worst case, I think, Q. I think in this problem, roughly C and Q have like the same upper bound based on the constraints of this problem. So in terms of the comparison, the log n heap solution, C log C solution is much more efficient. And that's kind of like the conceptual stuff behind this solution. There's a lot of like implementation details. I think most of them are honestly just easier to explain in the code, but just to kind of break this down for you guys, imagine we have like two connected components just to keep it simple. We want to have a min heap for each of them. So we want to have, like in this case, a min heap with 6, 7, and 8. And another min heap with 1, 2, 3, 4, 5, because they're independent components. Now, how exactly do we group them? Because let's say for a particular query, we get the node 6. Okay, we have 6, but how do we know if we have these two heaps, which of these heaps does 6 belong to? Well, we can give each of these heaps an ID. So let's just say this heap has ID 0, this heap has ID 1, and then as we're kind of building the heaps from the beginning, which is probably going to require some traversals of the graph, we can assign each of these nodes with the group ID. Like for 6, we can say, okay, it's going to belong to group 0. And then for 8, same thing, it's belonging to group 0, et cetera, et cetera. We can use a hash map to do that. It's pretty simple. And all of these, we can say they belong to group 1. And then when we have that group ID, that's what I'm going to call it, we can then use that group ID to find the min heap and then do whatever operations we want to do. Those are kind of the key points. Now let's get into the code, and it's going to be a decent amount of code. So I'll try to go through the boilerplate stuff pretty quickly. So the first thing I usually do is just build the adjacency list. I think if you made it this far into the video, you probably know what this does, but this is a default dictionary in Python. If you want to learn some of these Python tips and tricks, you can check out Python for Coding interviews on Leetcode. And then we're going to have a few variables, and that's going to be the key of this. One is going to be a hash set, which is going to track the online stations. And next, as I mentioned, we're going to keep track of the station group IDs. Going to use a hash map for that. Lastly, we're going to have a list of min heaps. Well, specifically in this case, a hash map of min heaps. So I'm going to again have a default dictionary where the default value is a list, because in Python, heaps are implemented with lists, kind of like in most languages, at least under the hood. And then I'm going to have a DFS traversal, and I'll show you how I'm going to use this first. First, what we want to do is run through every single station and start at every single station and do this for every station, which are going to be one index, so 1 to C+1, and we're going to call DFS. And we expect that this DFS is going to basically build the connected component that this belongs to, as long as this one hasn't already been visited. So online is also going to keep track of sort of our visited stations, because I could have just initialized this with everything from 1 through C+1, but I intentionally didn't, because I'm going to have this serve two purposes. It's going to track the online stations, but it's also going to, for the purposes of building the connected components, going to track the visited stations. So in here, we're going to pass in the station, but we're also going to pass in the group ID. What should I make the group ID? I guess I could track it with a separate variable, like I could use I, like this, and then on each iteration, just change I. But an easier way to do it would just be use the station itself, because every station has a different number. So if this station hasn't been visited before, we know for sure that the ID hasn't been used in terms of the group IDs. So just reuse that. That's the easiest thing, at least in my opinion. So we'll have two parameters here, station, group ID, and we'll check, has this station already been visited? If it has, we'll return. Otherwise, we will mark it as visited. Then we will say station group. We can map this station to the group ID that we passed in. And lastly, we can update the min heap that this one belongs to. So we'll go to min heaps, which is a hash map, we will use the group ID. It's possible that this is just an empty list. That's what default dictionary will do. And if it's an empty list, that's perfectly fine, because either way, we're going to run heap push on this, and we're going to push the current station. And then after we're done with that, all we have to do is use our adjacency list to get all of the neighbors of the current guy, neighbor in adjacency of the current station, and then run DFS starting from that neighbor. And you tell me, what should we pass for the group ID? Should we pass in the neighbor? Of course not. We want the current station and the neighbor to have the same group ID. So we pass in the original group ID. That's why we had two variables in the first place. If we were just going to make it the same, we wouldn't even have two of them. So there you go. This is just building the connected components. And once they are built, answering the queries are mostly pretty easy, just going to require a little bit of heap operations. So let's do this. Let's go through the queries, unpacking them. The first one is the type. The second one is the station. And we will check if the type is 1. Otherwise, we can assume it's 2, in which case all we have to do is say that this station is no longer online. That's easy to do. I'm going to do online dot discard. You can also do remove. I'm just not sure that, like, what if they give us a station that's already been removed? And if that's the case, remove is actually going to throw an exception, but discard won't. That's another little like Python trick. I think I do go over that in Python for Coding Interviews, or maybe even the Python for Beginners course. But in this case, we want to handle the more complicated case. We actually want to answer the query. So before we answer the query, let's initialize a little array for a result, and let's return that down here. So answering the query means that we want to find the smallest online node in the same connected component as this. Unless, of course, this one is actually online. That's the first case. Like if QStation is online, if it's in the hash set, well then QStation is the answer to the query. And then we can just continue to the next iteration of the loop. If that's not the case, now we're going to need to get into the heap. So to do that, let's first get the group ID, which we can get with our hash map. Did I call it group station group? So get the group of the current station. And using that group ID, we can get the min heap that this station belongs to. So we'll do that. And with this min heap, we're going to do pretty much what I said earlier. We're going to check while the min heap is not empty. And the root of the min heap, which we can get at index 0, is not in the online hash set. It's a not online. So we want the smallest one, but if it's not online, we have to remove it. We can do that with heap pop from the min heap. We're going to keep doing that until either the heap is empty or the root in the heap is now online. So we don't know what is the case, so we'll have to put an if statement to figure that out. So if min heap is non-empty, well then result has an answer, which is going to be the root of the min heap. Otherwise, it's going to be a default value of -1. Probably we could have done this with a ternary operator, but I don't really think it would make the code much cleaner. So I'll leave things as is, and you can see most of the code here. Most of it isn't really like crazy complicated. There just is a lot of the code, and it's pretty easy to miss an edge case. I believe in terms of the total time complexity, there's actually multiple parts, like building the adjacency list and even just traversing all of the connected components. That's going to easily be on the order of C plus, well, C is this, the number of nodes, and E, let's say, is the number of edges, and plus Q, we're answering every single query. And you might think that Q needs to be multiplied by something that we're doing in here, but that's actually not the case, because think about this. For each of these min heaps, we're only going to be pushing and popping each value once, like we're pushing here and then we're popping here. So it's not really dependent on the number of queries. It's just dependent on the size of each of these heaps. And that in the worst case, we'll have one heap, which is like of size C. So that in the worst case is going to be this plus C log C. So we can kind of get rid of that right there. So I believe this is the worst case time complexity. And here you can see that the code works. It is pretty efficient. I think there is one solution that is a bit more efficient, the union find solution. but I'd prefer this video doesn't become like 2 hours long, and this solution was long enough. And I think in most interviews, I think this would get you passing as well, especially if your code was like relatively clean. Anyways, if you found this helpful, check out Leetcode.io for a lot more, and I'll see you guys soon.